everybody. My name is Inon Lee. It is my privilege to give my talk at the 29th ITTC virtual conference on behalf of the Specialist Committee on Energy Saving Methods. Our committee consists of 7 members, as you can see here. Myself from Busan National University, Korea, and Dr. James Goss, this guy, University of Michigan, USA, and Dr. Andrea Corrado, University of Strathclyde, UK, and Professor Jianting Chen from China, and Professor Tie Li from Shanghai Jiao Tong University in China, and Professor Munehiko Hinatsu from Osaka University, Japan, and finally, Dr. Ramon Querada from Sejipa, Spain. As you can see here, we had 4 meetings in this term so far, and I'd like to express my thanks to the hosts of the committee meetings. Okay, here you can see the terms of reference from the 28th ITTC. Tasks are the survey of energy saving methods, reviewing and developing appropriate guidelines for CFD, model tests, and scaling. Full-scale data is important, and so we paid special attention to collect data regarding the energy-saving methods. This is the second term for our committee, so we are supposed to wrap up our efforts so far and hand them over to general committees in the 30th ITTC. Each chapter in the final report and this presentation roughly corresponds to each task. Okay, let me move on to chapter 2 regarding the survey of energy saving methods. Before proceeding to specific technique for energy saving, I'd like to summarize the whole category of ESMs, which are listed in the right in the table. As a matter of fact, this category was established at the previous term. It remains essentially unchanged. The primary category is about the principle, which means where the energy saving comes from. There are 4 primary categories regarding this. The direct reduction, the first one, and the reducing propulsive losses, the second, and followed by use of renewable energy and operation, which will be shown next slide. Each primary category is subdivided into specific mechanism, how the energy saving principle is achieved. During the present term, the committee searched for a new mechanism. So a couple of modifications have been made for the gate rudder and ducted control rotating propeller was added. Okay. This is the second page for the category of energy saving methods. And as I told you before, these are principles. Principles are use of renewable energy and operation. This is another general summary for the energy saving methods. This figure was taken from Bowman et al. In 2007. I'm sorry, I'm moving back. 2017, showing the performance of ESM in terms of CO2 reduction potential. Data was gathered from published work from 2009 to 2016. In this paper, the ESM are categorized into 5 groups, such as hull design, power and propulsive system, alternative fuels, alternative energy sources, and operation. Okay, the next slide is the list of sources for the literature survey. This list encompasses relevant peer-reviewed journals and conference proceedings. Articles mainly published from 2017 to 2021 have been reviewed and summarized for this chapter. Okay, this is the continued list of conference proceedings for the review. Okay, here comes the summary for each energy saving technique. First is the direct-to-direct reduction principle for frictional resistance. Most notable technique is air lubrication method with several papers published based on both model tests and numerical simulations. Another promising technique for skin friction reduction is to use low frictional coating. More and more interest are drawn to the effect of hard coating on the energy saving performance. Golo and Boskurt work in 2017 is notable in that they analyzed effect on hull coating on the full-scale ship performance for the 8 Ro-Ro vessels. Okay, others are also notable. And let me move on to the next slide. Okay, the next technique is the hull form optimization to reduce either viscous pressure resistance or wave making resistance. Okay, if the hull form in the after part is improved, then viscous pressure resistance is reduced, and the fore part is improved, then wave make resistance is to be reduced. Okay, this technique is closely related with the improvement of CFD technique and computing performance. So more and more researches are being carried out and published. As you can see here, the relevant keywords for hull form optimization is multi-fidelity meta-modeling, surrogate-based global optimization, and multi-objective optimization. And there are many literatures, and most notable example is that the hull form optimization is not only aiming at the come-out resistance, but also added resistance is to be reduced, as can be shown by Yu et al. In 2017. Okay, the next primary category is to enhance propulsive loss, reducing propulsive losses by either enhancing relative rotative efficiency or rotational efficiency. To enhance propulsive relative rotative efficiency, there are two examples as illustrated in these two figures. Okay, and of all the energy saving methods discussed in this presentation, perhaps the energy saving device would be the most popular ones to increase rotational efficiency. This subcategory includes pre-swirl stator or duct, rudder bulb, and rudder fin, PBCF, which means propeller boss cap fin, and contra-rotating propellers. And the most notable literature is the EU's GRIP, which means Green Retrofitting Through Improved Propulsion project, which was carried during 2016 and 17, and a special issue for reporting the results was published in International Shipbuilding Progress, volume 63. There are a few reports on the full-scale data regarding this project, so those papers will be reported in chapter 6. This slide summarizes the literature for pre-swirl duct. The most interesting example is Kim et al.'s paper in 2020, who emphasized the importance of roughness in the estimation of ESD performance at full-scale ship. Okay. For the pre-swirl stator, there are many researches carried out in a variety of organizations. Kim et al.'s paper, 2017, proposes an extrapolation method for analysis of a self-propulsion test with a pre-swirl device. Based on this result, the committee proposed a guideline for wake scaling method for pre-swirl devices, which is going to be adopted by this full conference. And this guideline will be explained in detail in chapter 6. Another interesting example is by Foreman's in 2017 with a special design illustrated in the upper right figure. Okay, the next slide is about the effect of combined energy saving devices. Two researches are worth being noticed. The first one is Lee et al. In 2017. They combined pre-swirl stator, tip rake propeller, and wave thesis rudder, and they reported approximately 5.5% of energy saving, combined energy saving effect. This figure appeared to be less than the sum of energy saving effect of respective devices. Another example is Hori et al.'s paper in 2017. They combined the rudder ball and duct, rudder fin and twisted rudder. They searched for an optimal combination of these devices, and the lower right figure shows how the delivered power is reduced by the possible combination of those devices. Okay, let me move on to chapter 3, titled as Use of Wind Energy. According to Parker, there are several types of wind energy system which is implemented. They are flattener rotors, kites or spinnakers, soft sails, wing sails, and wind turbines. Smith et al. 2016 stated that wind propulsion is most effective at slower speeds, less than 16 knots, and on smaller ships. The dead weight from 3,000 to 10,000 tons. Those ranges of dead weights account for 1/5 of global cargo ships. The typical energy saving effect by wind energy is reported to be up to 22 to 24% for a single flattened rotor, 1 to 32% for a towing kite, and 10 to 60% for the econo wind sails. However, there is indeed still a barrier to prevent wide adoption of wind energy solutions. These are the unfamiliarity with technology and safety and reliability concern and lack of demonstration. Therefore, we believe that more reliable full-scale data needs to be obtained to ensure the wider adoption of wind energy solutions. Okay, the next slide is a list the representative type of wind energy system and its energy saving effect. Wing sail was investigated by Viola et al. In 2015 and shown to reduce the thrust up to 10%. For towing kite, the percentage of fuel saving was predicted about 10% for Beaufort 5 scale, even higher, as much as 50% for wind velocities corresponding to Beaufort 7 scale. For flattened rotors, fuel saving ranging from between 5.6% and 8.9% were reported by these researchers. Okay, the next task for chapter 4 is to identify the necessity for new guidelines for CFD, EFD, and scaling methods. The first topic is about the CFD methods for energy saving device. The Tokyo 2015 CFD workshop is worth being noted. that was held at National Maritime Research Institute in Tokyo in 2015. The purpose of this workshop was the same as the preceding workshops, and it was to assess state of the art of the contemporary CFD codes for ship hydrodynamics. In this workshop, 3 ship hulls were selected, and a total of 17 test cases were specified by the organizers, and 30 groups worldwide submitted their completed results for 1 or more cases. Among those 3 ship hulls under consideration, the Japan bulk carrier case was associated with ESD. Actually, the dot as shown here in the figure. CFD simulations on resistance and self-propulsion performance were carried out either with ESD and without ESD. The validation and verification results drew attention of the committee because they can shed some lights on the overall level of accuracy of CFD simulation. A comparison of numerical errors between the case with ESD and without ESD would imply how adequately the state-of-the-art CFD simulation deal with the propulsive performance of ESD. That was the review topic number 1. And the next topic of Tokyo 2015 workshop is the statistics of CFD parameters, which can give an idea on the best practice of CFD. Okay, this slide shows a comparison error regarding the review topic number 1, comparison error in thrust coefficients and grid uncertainty for thrust coefficients. The first figure is about the grid efficiency, and the second figure in the far right is the comparison of percentage error in thrust coefficient with the experimental results. The major checkpoint here is to see whether the errors in ESD cases are systematically larger than those in no ESD cases. Okay, here you can see the error and uncertainty with the ESD is the bright gray, and without ESD case is dark gray. So you can see in some cases the uncertainty or error with ESD is larger, but on the other case, the opposite. So there's no evidence that the ESD cases lead to systematic larger error or uncertainty. So the answer is no, and there is no evidence to support the inadequacy of current CFD technique in dealing with ESD. Therefore, the need for a particular dedicated CFD procedure for ESD is not identified. Okay, the next slide is associated with the second review topic, the statistics of CFD parameters, a number of grids here, and the distribution of Wolf function, far right figure, the size of computational domain, minimum and maximum. And you can see there are wide variations in the parameters, okay? So the values for those parameters in our cases were compiled through questionnaire, okay? So there is wide variation in the parameters, which might cause the wide variation of errors associated, which is shown in the previous slide. Okay, the next topic is related to CFDs to review a proposed guideline in PROS 2016 conference. Hino et al. Presented benchmark data for the validation of CFD simulation results for a Japan bulk carrier with ESD in Tokyo 2015 workshop. The committee was aimed at identifying the necessity to set up a separate guideline dedicated to ESD simulation. So the committee had it had this proposed CFD guideline published in PRAS 2016, reviewed by CFD experts in academia and industry. The guideline section by Hino et al. Was compared with the following, the existing ITTC guidelines related to CFD. And we've got experts' opinion and concluded that, okay, some of the statements in the proposed guideline are not included in the existing guidelines. But on the other hand, it also can be said true that those suggestions are largely already well known in the CFD community. So it is hard to ascertain that the guideline by Hino et al. 2016 took into considerations for all the relevant aspects of diverse types of ESD because only a circular duct was dealt with. So the committee concluded that it is premature to set up a CFD guideline dedicated to ESD in the absence of reliable database of CFD as well as EFD results for various kinds of ESD. Okay, the next section in chapter 4 is related to the examples of new experimental methods for ESM. The first topic is for the test methods for PBCF and Rutherford, in which the usage of 3D printing technology in the manufacturing model ESD is noteworthy, as you can see in this figure. Okay, the next topics in the experimental methods section are the sophisticated arrangement of test apparatus for CRP pod propulsion system, which was published by Creda et al. In 2017. Okay. Another topic is the biomimetic approach to reduce skin friction, which was inspired by dolphin skin. Schroeder in 2018 conducted a coating test in the hydrodynamics and cavitation tunnel. This slide exhibits a couple of interesting model test apparatus designed to reduce the pitch motion due to waves, which consequently reduce the added resistance in waves. Chiu et al. In 2018 installed a pitch collapsing bow, fin energy saving device on a container ship model and verified the energy saving effect of about 4.29% by model test in waves. Yasukawa and Ishikawa studied a catamaran in waves by biologically inspired hydrofoil plate. Test carried out in calm water and regular head waves condition, and the maximum EHB reduction ratio by the hydrofoil was about 10 to 15%. Okay, let me move on to the next topic in the experimental method section. Skin friction reduction is one of promising techniques of ship energy saving, and air lubrication has been implemented in several tens of vessels so far. In 2017, the 28th ITTC adopted a recommended guideline to resistance and propulsion test and performance prediction with skin frictional drag reduction technique as a guideline to extrapolate the model test results to a full-scale prediction adopted by the previous full conference. However, the model test procedure for air lubrication in real practice has not been standardized yet, which may cause a significant deviation in the model test among model test organizations. So the committee was asked by advisory committee to give more detailed description of model test procedure on the air lubrication techniques, such as test condition, model scale pressure, and airflow rate corresponding to full scale. In line with this suggestion, the committee carried out a survey to investigate the current status of model test practices involved with air lubrication among organizations. 12-item questionnaire was distributed among relevant organizations, and 11 organizations organizations replied it. The following summarize the replies. Here we summarize the major questions in this presentation, so please refer to the final report for the full results. For the question number 4, the ship type considered, mainly bulk cargo carrier and tankers have been considered for the air lubrication. And for question number 5, scale factor, the majority was ranging from 10 to 50. Okay, the next item was injection pressure. In most cases, number 3 was selected, which means pressure was set at the hydrostatic pressure in Mother scale. Also, arbitrary pressure and no idea replies are also notable. And for question number 8, choice number 2 was mostly selected. The injection flow rate in the Mother scale was usually controlled to give the same film thickness as in the 4th scale. For question number 9, the choices varied between no extrapolation, ITTC 1978, and own guideline. So it is notable that the newly adopted guideline has not been selected. Okay, this again proves the absence of standard procedure related to the air lubrication model test. Okay, the next chapter is about the recommended guideline to be adopted in this full conference. It is titled as Scaling Method for Ship Wake Fraction with Pre-Swirl Devices. The purpose of this guideline is to complement existing ITTC 1978 for the ships equipped with either pre-swirl stator or pre-swirl duct. Okay, let me begin with explaining wake scaling issues of ITTC in 1978 related to pre-swirl devices. Pre-swirl devices can generate a counter-swirl flow to save rotational energy from propeller. For the prediction of powering performance, ITTC 1978 adopts the thrust identity method to find out the effective mean wake fraction. This is effective in the situation like figure 30A, but the difficulty in scaling arises from the point that the pre-swirl device makes not only a counter swirl, but also axial flow retardation. It is therefore necessary to decompose the axial and tangential components separately, as shown in figure 30B. The presence of pre-swirl device causes the relative velocity the propeller blade to change as UR prime with increased angle of attack, alpha plus delta alpha, and the thrust is increased. If the scaling is applied to the total amount of model wake based on the thrust identity in the ITTC 1978, this might result in overestimating axial induced velocity, UX prime, which is illustrated in, figure 30C, okay? So some remedy need to be made to solve this problem. Okay, the inadequacy of the ITTC 1978 scaling has led to the attempt to propose a new scaling in 1999. That approach, which is so-called ITTC 99, was based on the report, final report on the specialist committee on unconventional proposals. Okay, among two approaches, the method B, where the stator is considered as part of the hull, is now commonly referred to as ITTC 1999. The major difference compared with the 1978 formula is this term, okay, WMS minus WMO. Here the stator action was considered to be mainly of potential nature because the main effect of stator is to increase the angle of attack of the propeller blade. Therefore, the difference in wakes with and without stator is directly transferred to full scale. Well, even though this might be more reasonable than ITTC 1978, but this can account for the viscous nature of axial retardation. Okay, so with a view to improve both ITTC 1978 and 1999, there has been a series of researches in which axial wake and tangential wake are separately treated according to ship type and device type. Okay, for instance, pre-swirl duct is adopted for fuller and slower ship like tanker, and while pre-swirl stator is employed mainly for slender, faster ship like container carrier. Kim et al. In 2017 presented that the portion of the increase of angle of attack by axial and tangential flow is different for pre-swirl stator or pre-swirl duct. They proposed this scaling formula shown here. Okay, this is a compromise between 78 and 99 in that the axial velocity component and tangential velocity component are scaled separately. The axial wake, being of viscous nature, is scaled following ITTC 1978. On the contrary, the tangential wake is scaled after ITTC 1999. It was found that the portions of tangential and axial velocity vary according to the vessel type as well as the device type. As shown in this table, it was proposed the factors of axial and tangential portion to be 0.3 and 0.2 and 0.8 in PSS and PSD cases respectively. It's worthwhile to mention that the factors in table 2 in this table have been derived from limited ship types, KCS and KVLCC. So a generalization toward identifying a reasonable value range for each factor based on more studies is necessary. Okay, that was the recommended guideline. I'd like to summarize the full-scale data. The importance of full-scale data in proper assessment of ESM cannot be overemphasized. However, full-scale data for the ESM is very little, so we always need relevant full-scale test campaign for energy-saving methods. I'd like to summarize the full-scale data published in open literature. The first category is energy-saving device, and the most notable literature is Haselara and Yan in 2017, who reported the sea trial results with and without the pre-swirl stator and compared with full-scale simulation results. This study was carried out as a part of EU's GRIP project, which was introduced before, and from 2011 to 2015. And as you can see in this speed power curve, 6.8% energy saving and trial condition was reported. Vienke showed 4 examples of the PVCF and one duct. Model test sometimes overestimates power saving effect for different draft. And Themalis et al. Reported Mavis duct led to saving of fuel oil consumption by 3.5 to 5%. Okay, the next topic of direct reduction is by air lubrication and low frictional coating. De Freitas introduced full-scale data of air lubricated 40K chemical tanker and showed about 5% saving on the average. Okay, and the next topic is low frictional coating. Cho et al. Carried out ISO 19030 analysis for in-service performance of 76K bulk carrier, and it was found out that the speed increased by 3.7% due to the frictional reducing coating, which is equivalent to 11.7% power saving. Okay, this is the last slide, and Here we summarize a potential task for the next committee. And number one is continue to monitor the development of relevant technique for ship energy saving and identify the needs to complement the present EEDI framework. Number two, identify the necessity of guidelines for CFD methods, model tests, and scaling for energy saving devices. Number three, continue to collect full-scale data obtained through relevant benchmark tests. Those were the potential tasks to the next general committee. And finally, I'd like to recommend to the conference the 29th ITTC Specialist Committee on Energy Saving Methods recommends adopting the new guideline on scaling method for ship wake fraction with pre-swirl devices. Okay, that's it. That concludes my presentation, and thank you very much for your attention.